So welcome to the San Mateo County Astronautical Society meeting and our general meeting and our talk. This club's been around since 1960, and we've had lots and lots of presidents over that time. And one of those presidents is someone who's going to talk to us tonight.
I was a VP.
Oh, you were a VP? You
Yeah,
were a president?
No, I'm not president material.
Oh, God. Okay, so VP.
Get the job done.
So VP. I'm sorry, I thought you had a good president for a while.
No.
All right, but VP. So, for those of you who don't know, if probably most people already know, Saint Nick here, Santa Claus. Does everybody know me?
Yeah.
Okay. I'm also known as Michael Cooke, the club president. Okay, so he's been a member of our club for like 20 years, and like when he gets into stuff, he gets into stuff. So not only, has he been a member of the club, helped run the club, but he's created his own observatory in his backyard, which was pretty cool. And he has a whole website dedicated to some of the stuff that he takes pictures of, which is called Green Hawk Observatory. And so you can visit greenhawkobservatory.com and see a lot of his cool pictures, and he sometimes puts music to them, and you can see a lot of his work, and a lot of it's just done, in his backyard in San Jose. He's also a member of the Fremont Peak Observatory Association, and he's certified to run the 30-inch Challenger telescope. Yeah, that's pretty cool. So, I won't talk about his professional life, but he's also a rock star in that with many of his cool companies. But we're here about his super big knowledge on astrophotography. And if I got the story right, correct me if I'm wrong, you started off not knowing a lot.
No, knew nothing.
And within 20 years, he's cranking out award-winning photos. So he's got a lot that he can teach us today. And we've used a lot of his pictures. He's on our new postcard, and he's all over our website with pictures. So give a current board member and former VP Chanan Greenberg a hand. Warm welcome.
Thanks, Mike. Just checking, can you hear me okay?
Yep.
All right, volume's good. Excellent. So, hi everyone. It's a pleasure to be here tonight. And before I get started, I actually want to do a quick dedication. So, if I can just get my clicker to work, that would be even better. So there we go. So many of you who are members of the club know that this past year we lost a couple of really wonderful people, Ed Pieret and Dr. Ken Lum, who are long-time members in the society, longer than me. And in my 20-plus years with the society, these two very fine gentlemen offered me their friendship and their support and their guidance as I went through my journey of learning about astronomy and learning about astrophotography, and they always offered a lot of encouragement and help. And so I'd like to dedicate tonight's talk to Ed and to Ken. So let's talk a little about what we're going to cover today. We're going to start with kind of sounds like a strange question given the topic of today's presentation, but why bother with astrophotography? Given the fact that today you can just go online and find phenomenal images for free, why do this? And I know we have various people here with smart telescopes and astrophotography rigs, and I'd like to open that up and see what what drives the madness of people to go and explore this hobby. We'll then talk a little about what we can see in an image. I call this seeing physics, because it's not just about taking pretty pictures. It's actually looking at what's going on inside the image and actually being able to understand what's going on there. So I've taken a sample image, and we'll do a quick dive into the physics of what's going on in that image. We'll then talk a little about the different flavors of astrophotography. Today you can do astrophotography in many different ways. You can use your smartphone, you can use a digital camera, you can use a smart telescope or electronic telescope, and you can obviously use dedicated cameras for astrophotography. So we'll talk a little about the different capabilities of these different options. And then we'll talk a little about what does it actually take to capture different kinds of images. What does it mean to capture a picture of the Milky Way versus a picture of a solar system object versus a deep space object. And then we'll go into a tutorial about image processing. And we'll actually focus on deep space image processing, and we'll go through the various steps there. And we'll touch briefly on solar system objects as well. When it comes around to this tutorial, one thing I'd like to call out, it is not focused just on people who have dedicated astrophotography cameras. Everything we'll be discussing will be applicable to people who have smart telescopes or digital cameras. So hopefully this will be something that will be useful for everyone. And for those who have none of these things, at least it'll give you an idea of how do we create the magic of capturing these deep space images. So with that, let's get started with why bother with astrophotography. For the last 30 plus years, we've had internet in every home, thousands upon thousands of extraordinarily high quality images available from a wide variety of different telescopes, the Hubble, the James Webb, the new Vera Rubin. There's no hope for an amateur like me to compete in the quality with those images. So why do it when you can just go onto Google and search any image you want and find it in very high quality? And I'd like to open this up to people who do astrophotography here in the room. Anyone want to venture why you bother? Why do you deal with the cold weather and the expense and the frustrations and learning curves and all that? Why do you do it? It's a journey, okay. Satisfaction. You have a gluttony for pain, eh?
I just enjoy all the engineering trade-offs. And
Okay.
it's sort of like hunting, not a hunter, but it's like you're going after something. You have to make all the right decisions.
I'll just repeat this for everyone. Going after, like chasing something or hunting something, and also overcoming technical or engineering challenges. What other things motivate people here to go and do that? Yes?
Because it's something you did yourself.
Something you did yourself. Well, you guys have clearly been reading my slides. Because this pretty much sums up what motivates me, and I'm going to share that in the next slide, which is doing it yourself. I call it the tourist syndrome. If you went to Yosemite, let's face it, Yosemite's been taken images by everyone from Ansel Adams to everyone who works for National Geographic. The world doesn't need another picture of El Capitan, all right? And yet, when you see it and something inside you moves and excites you, you take that picture and you share it with all your friends and family. There's something about that experience you had that you want to share with other people, and you want to preserve the memory of that. And astrophotography is not all that different. If you have an interest in astronomy and you saw something really cool, you want to be able to keep that. You want to be able to show people, look what I did, look what I saw. So that's definitely one motivation. The other is the technical challenge. There's lots of different skills and capabilities that you gain over time as you learn to do astrophotography. And if you are into those challenges and overcoming them and achieving, then that makes you feel good. And last but not least, and it may be phrased a little strange, but I like the way you phrased it, the chase or the hunt. To me, it's like there is it's a direct connection to the universe, because you are reaching out with your equipment and grabbing those little packets of energy, those photons, that light that could be thousands of years old, it could be billions of years old, and you caught it and you imaged it, you processed it. It's an active engagement. It's not a passive experience of looking at some picture that somebody else took, the Hubble or something else. So these are the things that engage me and the things that excite me in terms of why I still do astrophotography, why I still enjoy it when I get around to do it. So let's talk a little about what we can see in an image. And I'm going to start with, I just took a sample image of something I took about 1.5 years ago. This is the, I hope you can see it okay. A bad angle here. This is the Dumbbell Nebula. And it's called M27. It's a planetary nebula. I'll explain a little more about that, although I think most of you don't need the explanation, but I love talking about it, so I'm going to do it anyway. Just a few technical notes about this. This was a 4-hour exposure using a 5-inch refractor from a very light-polluted backyard in San Jose. So now, for those of you who do observational astronomy, and you've looked at the dumbbell nebula using an 8-inch or a 6-inch telescope, and what we typically see is that little gray smudge that kind of looks like an hourglass or a dumbbell. Well, what we're looking at is all the green material. That's what we're seeing when we're looking at it visually. When you put on an O3 filter to enhance the view, what you're enhancing is the oxygen data in this image, which is the green or teal color that you can see here. All the red stuff that we can see in this image, you do not see visually. And that's one of the things, again, that I think is pretty cool about astronomy, which is, astrophotography, which is allowing us to see beyond what a real-time image through a refractor or a reflector allows us to do. Now, what I'm going to do now is I'm going to sort of crop out and focus on the center of this image to really show the details of what we can see here. So as I said, this is a planetary nebula, for those who do not know. A planetary nebula is basically what happens to a star like our sun when it dies. Okay? Small stars like our sun don't explode in a big supernova at the end of their life. They go through a very different process. And so we're going to explain a little bit about the physics. Stars like our sun can happily chug along for billions of years, and the existence of that stable star is based on the balance between two forces. You have gravity, it's trying to crash everything down to the center, and at the very center of the star, at the core of the star, there is nuclear fusion. It is so hot and so dense that we're smashing hydrogen nuclei into each other and we're fusing them. We're doing nuclear fusion, releasing a huge amount of energy that is trying to burst outwards. When you have a balance between these two forces, you have a stable star. But it doesn't stay like that forever. After, let's say with our sun, after about 10 billion years, what's going to happen? In our case, it's in 5 billion years from now. The core of that star is starting to build up a ball of helium. When I'm fusing hydrogen into a heavier element, I'm creating helium. That helium is not really doing much. It's just sitting there in the core, in the center. And around it, I have a shell of hydrogen that is still fusing, and then the rest of the star that is just hot. But as the core contracts, it gets hotter. And when you increase temperature in nuclear fusion, you send it into overdrive. Now, the nuclear fusion energy that is being produced is so much that it is not, the star is not big enough to shine it all away. So it's converted to kinetic energy, and it starts pushing the envelope out, creating what we call a red giant. Red giants will last typically between hundreds of millions of years to about 1 billion years. And the core continues contracting until it reaches about 100 million degrees Kelvin. Now it's hot enough for helium to start fusing, and we're now fusing helium into carbon and a little bit of oxygen. So we now have a core of carbon and oxygen, which is inert, it's just sitting in the middle, with a shell of helium fusing around it, and a shell of hydrogen fusing around that. Now this is an unstable process. Especially with helium, it's very, very sensitive. Helium fusion is very, very sensitive to temperature changes. If I increase temperature by 1%, as the core contracts, I'm sending nuclear fusion 40% up. So 1% increase in temperature will send nuclear fusion into 40% increase. That is what we call a helium flash. Okay, for a short period of time, there's a huge amount of energy that is now coming out from the core. And because, again, it's not going to be shined away, it's kinetic energy that starts pushing the envelope of the star away. And we have another flash and another flash until we end up with an exposed core, which is that carbon, oxygen, white dwarf, and all the other gases that made up the star are moved away. And this is what we're seeing in this image. So all these gases that we're seeing are what used to be part of the star and got pushed out. So we can see this physics playing out in the image. We can see the gases being pushed out from the star. We can see the white dwarf in the middle, and this is, by the way, white hot. For comparison's sake, our sun, the surface temperature of our sun is roughly around 5,000 degrees. The temperature of this white dwarf is around somewhere between 85,000 to 160,000 degrees. So it is extremely hot. It's shining and letting off a huge amount of ultraviolet radiation. And that ultraviolet radiation is interacting with the gases around it. And it's stripping away electrons. It's ionizing this gas. So when you take ionized hydrogen, which is now just the proton, and you recombine it with an electron, that process lets off a photon of light. That's light that's being released, and the wavelength is red. So what we're seeing, this red stuff that we're seeing, is the hydrogen recombining. Same thing happening with this green, blue, teal color, that's oxygen recombining. Again, it's stripped away from electrons, recombining with the electrons, and it's letting off this little green light. Another thing that we can see in this image, if you pay attention, there's solar wind that is coming from the core and colliding with these gases. It's really pushing into the gas in the medium, and that is colliding with gas that is further out. It's creating these little clumps of gas. So we are seeing basically the stellar wind affecting the gases around in the nebula. And last but not least, if you pay attention, you can see this sort of axis of a red line coming down here and very prominent up here. And that is basically the hydrogen gas that is being pushed out by the stellar winds, but it is aligning with the magnetic fields of the white dwarf. So these jets are created by the stellar wind and the magnetic fields. That is a lot of physics to see in an image. And again, to me, this is one of the exciting things. Admittedly, I'm a bit of a geek. So I think it's pretty cool that we can see all this stuff playing out in an image that was captured by a 5-inch refractor from a backyard. This is an example of the kind of things you can see. And every image in astrophotography has a story like this to tell. It could be the death of a star, it could be a stellar nursery where new stars are being born, it could be a galaxy. Every one of these images actually has a story and information behind it, which I love to read and learn about, and makes it very interesting for me. Any questions about this before we go any further? All right.
Question over here.
Sorry, I didn't see that. Sorry.
How exactly did they find out, like, originally how nuclear fusion takes place with hydrogen?
That's a great question. So I'll try and answer it succinctly because I actually do give a presentation in about 2 hours about that one question. But the simple thing is, way back in the 19th century and before, they didn't know about nuclear fusion. They assumed all sorts of other things. They thought it was a big ball of coal that's burning in the sky. Forget the fact that there's no oxygen there for burning, but there was a lot of different assumptions. They thought that it might be asteroids and comets smashing in and releasing energy. Ultimately, it was the beginning of the 20th century when we discovered radioactivity, and we discovered that if you take 4 atoms of hydrogen and fuse them, you will get helium, and you will lose 0.07% of the mass converted into energy. Now that doesn't sound like a lot, but when you take that small number and put it into Einstein's equation of mc squared equals energy, when you take even a small amount of mass and multiply that by the speed of light squared, it produces a huge number. And they came to the conclusion that that is probably the mechanism that is driving energy creation in the heart of a star. To prove that, we had to find something, and in this case it was the byproducts of this burning. One of the byproducts that is produced in the nuclear fusion are neutrinos. And so we've built neutrino observatories that have been able to actually capture the predicted amount of neutrinos coming from the direction of the sun. And so we've now found pretty solid evidence that this is the mechanism that is happening in the heart of the sun. It's a great question. Okay, so let's go on then. And by the way, we've got Daryl here, so if I'm speaking nonsense, feel free to correct me on that.
You're doing great.
Thanks, buddy. Okay, so let's talk a little about the different flavors of astrophotography and what we can do. I'm going to start with smartphones. Smartphones today, you can do almost anything with them. You can put them on a tripod, and using the native standard low light imaging, you can do images in a dark location, obviously not from the Bay Area, of the Milky Way. You can do images of moonlit landscapes. You can do time lapses of eclipses, lunar eclipses, and solar eclipses. You can attach them today directly to an eyepiece in a telescope and take images of the sun and the moon, I would say that deep space images and planets might be a little bit of a challenge. So I wouldn't build on using that as my tool for doing images like that. The example that you have up here, that was just me trying to see if it could be done. That is the International Space Station, moving at a speed that is faster than the speed of a bullet at 400 miles away from me, captured with this iPhone. All right? So you can do pretty cool things. This one I just strapped it onto my 12-inch Dobsonian. And one of the things you can do, and I highly recommend it if you want to experiment, is you can buy apps that give you full access control into the camera that's inside this phone. The standard out-of-the-box camera applications on your phone are actually limiting your access because they're trying to automate a lot of things. And in astronomy, we actually want more control. So with these apps, I think one of them is called Moments, is the one I use, you can basically have full control as if this is a DSLR camera. You can control the ISO exposure, you can control the shutter speed, you can control any light enhancement, you can literally do anything you want. And so here I had to set the shutter speed to something like 1/8000 or something crazy like that. It was a very, very fast exposure. And I was just manually tracking in the sky, because this thing moves fast, right? So I had it in my finder, and I was looking in the finder and tracking it in the sky. The phone was connected to the scope. I just told the application to take images. I think it took about 1,500 images. And while it's not a great image, I mean, you can make out the solar panels, but it's not exactly a sharp image. Still, that's 400 miles away, moving at faster than the speed of a bullet. That's not bad for an iPhone. So you can do a lot of fun experiments with iPhones. The next one is digital cameras, and basically that is by far the most flexible platform for photography. Number one, because it's versatile. It's a regular camera you can use for different goals, but you can do nightscapes and Milky Way and moonlit nightscapes and again time lapses, and you can attach it to a telescope and do deep space. There isn't much you can't do with a digital camera, whether it's a DSLR or a more modern mirrorless camera. There's quite a lot that can be done with these. I'm going to show you now a couple of examples of time lapses I did with a digital camera. The first one is basically a transition of night to day, day to night, taken from Fremont Peak. And I chose my timing really poorly because of all these clouds, and there was also a star party there, so my camera, as you'll see, got bumped twice by a couple of kids. But it still actually shows you a really nice transition from daytime to nighttime and the rising of the Milky Way as the Earth is rotating. So you can actually see the rotation of the Earth as the... That's weird. What was that?
1950s horror.
Yeah. This is the Twilight Zone. All right, so let's see this video play out. I apologize, it's a little chunky because it's being broadcast over the internet onto this projector, so it's not as smooth as it should be. And soon you'll see the Milky Way rising here and moving in this direction. There we go, that is the Milky Way. And this was just still images taken with a Nikon camera.
Was that taken from the Great Left Peak Observatory Association's office?
Yes. So the next one is going to be a time lapse of the last solar eclipse, the total solar eclipse from last year. And this one I'll let it play out first. So I used a Nikon Z7 Mark II camera, and this video is made of 1,300 individual still images that were then stitched together into a movie. You can see this is first contact with the moon starting to encroach and cover the sun. The whole first phase was taken through a solar filter because I'll fry the camera and the chips and the optics and everything if I'm imaging the sun. But you'll notice that as we get to totality, or just before totality, when there's just a little sliver of the sun left, I remove the solar filter. and just even that little less than 1% of the sun just burns out the image. But you'll see we'll see the diamond ring, and we'll see totality. And I'll explain a couple of things about totality when we get there. And this is, of course, it was over 2 hours, so this is all condensed into about 3 minutes, start to finish. And the solar filter came off, and it looked like there was no sun left, and just look at how bright that is. And we'll soon be arriving at totality. Prominence down there that later will appear much bigger. There's a little prominence up here as well. Now we're in totality, and what you'll see now is I took a series of different exposures at different lengths, and the reason is that what we're trying to see here is the corona. Think of it as like the atmosphere of the sun. The inner corona is extraordinarily bright, and the further parts that are further away from the sun are very, very faint. There is no way to image that in a single exposure. So you have to do a series of exposures of different lengths, going from very, very short to longer, roughly 4,000 up to about 1 second. And as you can see, when you get to 1 second, it almost burns it out. Then you blend them, and this is what the corona looked like during the eclipse, which is a pretty nice image. You'll notice now this very huge prominence. And this is a live image, so you'll soon see the sun appearing right over there. And even after it appears, you can still see the prominence. It's pretty cool.
Is some of the chromosphere visible around the time?
No. Well, maybe a little bit, tiny bit, yes. Now I have to put the filter on again. So this is again a nice little play with a digital camera. In this case, doing a time lapse of the total solar eclipse. There. Okay. So this is the setup I used that day. So that is the digital camera, the lens, and the solar filter running on an iOptron Skywatcher tracker, so it's tracking the sky, tracking the sun. And it's connected to a laptop, so this entire process was fully automated with a script that I wrote. So I didn't have to touch this. I was looking at the eclipse and enjoying the eclipse, and all the changes of exposure and all that were pre-configured and automated. So I didn't want to mess around with equipment during the eclipse. This is another picture taken with a different camera. This is a Nikon DSLR, and this was with a 10mm lens. I wanted a wide field view. It's not a good focus, unfortunately, but you can easily see Venus over there. I want to remind you, by the way, this is 11 o'clock in the morning.
Yeah.
Okay, so this is Venus. Jupiter was way up there just outside the frame, so didn't catch that. And of course, this looks like a sunset. What it really is the 360-degree sunset you get during a total eclipse when you're under the shadow of the moon. So it's a pretty cool experience. If you've never seen one, go see one. Yes, sir?
Yeah, in terms of scripting the telescope, did you have to figure that all yourself, or are there libraries up there that tell you?
It wasn't a library, but there's a standard tool that is designed to control the digital camera, and they can work with the new modern mirrorless ones as well as the DSLR ones, and you can just write your own script in the application, and I did that. And there's no coding involved. I mean, writing a script sounds a lot more intelligent than what it really is. It's simply saying, do 10 exposures at this ISO at this length, and once you've done that, do another 5 exposures, and then it's saved as a script, and then you just hit play, and it goes. Yes?
How did you sequence the filter swap?
The filter swaps I had to do manually. So taking off the filter, I had a timer that told me now, And I just went, and I could also visually see because I was looking with protective glasses, so I could see, okay, we're almost there, and that's when I just took off the filter. So I took off the filter and then let it do what it was doing. When I was done, I put it back on again.
So did your laptop screen, like say, a big now or something like that?
No, I just look visually. I mean, by the way, there are apps that do that. And I saw an iPhone app that actually tells you all your sequencing of how you should image the eclipse. I tried to use it. I found it very confusing and just decided to do it my way. Okay, so let's move on now, and we're now going to talk a little about, actually a lot about, smart telescopes, electronic telescopes. By a show of hands, who has a smart telescope here? Yeah, we have quite a few, and I have one too. So we'll talk a little about this, because I think it's a really fascinating space. Now, a lot of us have been familiar with the unistellar EV scope, which came out 4 or 5 years ago, and after that there was a plethora of more solutions that came out, which we'll talk about in a minute, but they weren't actually the first ones to come to the market with an electronic telescope. The first one that I'm aware of that came to the market was actually Meade with their ETX-LS telescope that came out in 2008. They had a 6-inch version, and then later an 8-inch version, and it had a built-in camera. It had a 3-inch monitor that allowed you to see what was going on. The camera was able to do its own alignment, so just like the modern smart telescopes do, it could analyze the sky, do its alignment automatically. You could take wide field views of constellations. You could take solar system object images, but when it came around to deep space, not so much. It didn't have all that rest of the packaging for stacking and all the other cool things that we have in the new smart telescopes. So it was kind of strange because people want to do the cool deep space stuff, getting galaxies and nebulae. It couldn't do it, and yet the price tag was somewhere between $6,000 to $8,000, and so it didn't really find a market, and this one fizzled away. But they were the first ones that actually packaged something and brought it to the market. Very sad story about Meade after they got acquired by Orion, and then Orion went belly up. So all that technology is not owned by anyone these days. Anyway, today we have a lot of options. And you can see here on the right-hand side, this is the Vespra. Over here we have the Unistellar, which has various models. There's the Dwarf telescope, which I did not put up here. Then there's the Sea-Star, and over here is the Celestron Origin. And what's kind of interesting when you look at this market is that from a price point standpoint, the Sea-Star and the Dwarf are both below $500. Then all the rest of the options are somewhere between $3,000 to $5,000. So there's a gap there in the middle of this market, which is currently not being served, and it's probably going to be served really soon by ZWO with their next Sea-Star release, which is probably going to be somewhere priced between $800 to $1,200. It's going to have some incredible features. So I'll talk about that a little later. These telescopes are absolutely revolutionary, and I'll soon explain why, because they've really removed the barriers to going into astrophotography. That used to be a pretty high bar with a pretty steep learning curve. You really don't need to know anything other than switching an on button and then using an app on your phone. And if you're capable of doing those two things, you can do astrophotography with these tools. Now, there's differences. There's differences that are really material. The aperture of the Dwarf and of the Sea-Star currently, and also I would say of the Vespra, limit what it can do. So at this point in time, the unistellar telescope with a bigger aperture is able to show more details, more color than those scopes, and I would say still has an edge on. However, when it comes around to virtually every other feature, they're going to be giving it a run for the money because the software is better with these applications, with these scopes. This little guy is an apochromatic refractor. That's good optics. Okay, and that is, it's small, it's 50 millimeters, but it's actually quite impressive to be able to do that. And so there's a lot of innovations, mosaic capabilities, things that right now Unistellar is starting to fall behind from a software standpoint, and I'm hoping that they step up. However, that said, and with all due respect to all of the scopes here, after watching a few sessions of the Celestron Origin, which is this guy over here, I was absolutely blown away. And I think that, at least at this point in time, this is by far the best solution in the market in terms of the quality of the optics, the quality of the image, the quality of the processing. It just knocks every one of the other scopes out of the water at this point in time. And if Celestron continue investing in it, it can continue to evolve. So let's talk a little more about what these scopes can do. So what you can see here are sample images. Now these were taken with my EV Unistellar telescope, and this is the original 1.0 version, so it's the simplest version out there, a pretty old one. You can see here an image of the sun. This is an image of M27, the Dumbbell Nebula that you saw earlier. This is an image of NGC 891, which is a galaxy roughly 30 million light years away, and this is the Whirlpool galaxy about 23 million light years away. And I'll say this, 15 years ago, I want to point out something. This is a 15-minute exposure. That's it, 15 minutes. Now, if you were to think of 15, 20 years ago, what I had to do to try and produce an image that looks like this, I'd have to spend an hour and a half setting up my gear, balancing the scope, polar aligning, all that other good stuff. Then I'd have to spend an hour or two on imaging. Then I'd have to spend another possibly hour or two on image processing. And again, my equipment was limited, my knowledge in processing was limited. I probably wouldn't have produced at that point in time anything better than this. And that was done in 15 minutes. That is pretty revolutionary. And if you think about what we needed to know, what we had to do before we had smart telescopes, that curve, that learning curve was pretty steep, because we had to know how to match our scope and the chip of our camera, because that would affect the field of view and the resolution of what I'm imaging. So not every scope and every camera are a good fit for the target I'm trying to image. So you'd have to figure that out. You'd have to know how to physically balance a telescope, because it needs to track properly, and if it isn't balanced properly, it won't be able to track the sky correctly. Polar alignment, boy, that can be fun. Today, not such a big deal. We have these little cameras on front of the mount, and within 5 minutes you can get pretty good polar alignment, so you can track the sky fairly accurately. Before we had those things, 10 years ago, 15 years ago, you'd have to do a thing called drift alignment. Now, drift alignment is basically taking an eyepiece with an illuminated reticule, like a crosshair in the middle, and you're looking at a star, and you are stuck glued to your scope and waiting to see if that star drifts. And if it drifts, you have to figure out in which direction you're supposed to correct your azimuth or altitude to get your scope corrected. You could spend a couple of hours just doing that. And then on top of that, you need to get all the software working. You need to have your planetarium software with your imaging software, with your autoguider, all working in conjunction with each other. Or drivers sometimes didn't collaborate really nice, so the software was a little kludgy. And last but not least, you had to learn all the image processing steps to get your final image out. That was a lot to learn, 15, 20 years ago. You don't need any of this. These scopes have made all this redundant. So it's absolutely revolutionary in terms of what the lowering the bar for people who want to come in and try astrophotography. Now, you can go and debate on the quality of the image and things like that, but I would say today, if anybody is starting in astrophotography and wants to try it out, go and spend $500 on one of these things, or if you want to go crazy, spend $2,000, $3,000, and play around with it. Once you're getting so good with that you decide you want to do more, go ahead and splurge on a dedicated system. But this is definitely the easiest, fastest way to get into this hobby. Now, pointing again to this image of the Dumbbell Nebula, this one was captured with the UV scope. When I compare it to the image I got with my dedicated camera, it's a different ballgame. Right? This is a better image, hands down, less noise, a lot more detail, a lot more finer, granular information in the image. Definitely not comparable to this. Okay, but I want to remind you, that was a 4-hour exposure, and then I also spent hours in processing the image. This was 15 minutes. Okay? So there are limits to what these scopes can do. So let's talk a little about the pros and cons of these scopes. The pros, first of all, close to zero setup time. You literally connect it to a tripod, put it outside, and press one button, you're ready. It's ridiculous how easy they've made it. Very easy to use. If you can use an app, any other app on your phone, you can use this app. It's not complicated at all. Near real-time viewing is pretty cool. I don't have to wait for hours to capture my image and then hours more to process. In real time, as the image is building up, I can see it. That's actually pretty cool. It does, it's easy to share. It's already on your phone or your tablet, so you can just send it and share it to anyone you want, and virtually no learning curve. These are all the pluses of these scopes. But they do have some drawbacks. Now, they're not all uniform for all the types of telescopes, so what I'm doing is sort of a common denominator, and I'll make a few call-outs to explain things. First of all, you have limited optical quality. Now, this is not the same for all the telescopes. The Origin and the C-Star actually have pretty good optics. Unistellar, not so much. Okay, so I would say that the optics of the Unistellar is less than the average reflector. Not great. And that is a physical limitation on what you can get from your images. If the optics are not good enough, then you're just not going to get good enough data. Secondly, limited focus control. So again, the C-Star and the Origin do actually have automated focus control, which is really cool. With the Unistellar, you have to use this batten-off mask, and your hand controlling the focal points. It is virtually impossible to get to really accurate focus. Just to give you some perspective, in my dedicated rig, and I have a nice refractor, just the focuser element, just the draw tube that moves the camera, that's about $1,400. Okay, that is a well-machined piece of equipment that, when connected to an electronic focuser motor, you can get sub-micron level motion to really bring it into perfect focus. None of these scopes can do that today. Okay, I emphasize today. That may change. So when you have limited focus control, limited optical capabilities, there is just a limit, a physical, actual limit of what you can get out of the image. Image processing is kind of interesting. So as these scopes are taking the image, they're showing you the image in real time, and then you save it, and you have a JPEG on your phone. And because you get a final image sort of given to you, most people actually don't do processing. Or, worse, they make the mistake of trying to take that JPEG and process that, but a JPEG is not a file you want to work on, because you've just deleted, the JPEG is a compressed image, it's deleted 90% of the data. If you try and do any enhancements, you're going to create really strange artifacts. So you don't want to do that. Now, most of these scopes have the raw data. You can access the raw data, download it to your machine in FIT format, which is raw format, and then you can do the image processing that I'll be showing you here. But I don't know many users who actually go and do that, and I think that's a missed opportunity, because there might be some great images hiding there that you just didn't bother processing the data correctly to show them. So I think that's something that people should consider doing. When it comes around to solar system objects, they're so bright, they kind of overwhelm the chip, and they try and do sort of real-time imaging when lowering sensitivity, and it's okay, but I mean, it can't hold a candle to what you can see with just a regular refractor telescope. Forget cameras. It just doesn't come close to what you can see there. And the same applies to star clusters. With star clusters, when you look at, when you're looking through a regular telescope, refractor or reflector, stars are points of light. And it's a very pretty view. When you look at a globular cluster through a regular telescope, you're seeing like a pincushion of all these points of light gathered together there. And when you look at it through a smart telescope, and you can see the stars in my images here, they're kind of bloated and they're not even very round. See, there we go. And they're not very round because the chip gets overwhelmed. The chips have sort of a full well capacity. Every pixel has a certain amount of light that it can gather. And when a pixel collects too much light, the extra light spills over to the adjacent pixels. And that creates this blooming or this blotting of the stars. So it's just not a great view. And again, something that could be fixed with software. The C-Star seems to do a better job than the other telescopes in this area. So far, most of them don't handle that very well. And last but not least, there is, go ahead.
the origin will, the final image, run a deconvolution that's based on a machine learning algorithm.
That will help.
And it really pinpoints the color.
I'm sure that
Very
will
good
help.
for clusters.
I'm sure that will help. So again, the origin again is proving to be so far the better platform. I totally agree. Last but not least, you have field rotation, which basically to track the sky correctly, you need to, the sky moves in an arch. You need to have an equatorial mount that mimics that motion. These scopes are all on altitude azimuth mounts, and they don't track it the same way. So if you did really long exposures, which is what you really need for good deep space images, then you're going to get field rotation. You're going to have your object and all the stuff around it is going to be warped and creating trails. So these are limitations. Now, by the way, I should mention that most of these scopes have equatorial wedges. So you can actually convert them into an equatorial tracker. But again, I don't know anybody who's actually doing it. So, that solution is available. I view all these limitations right now as temporary. I think that as newer versions are going to come out, new capabilities and new improvements are going to be there, and some of these things are going to go away. If I think about the next, and this is just rumors that I've been reading online, about the next C-Star 70 telescope that's going to come out, that scope, among other things, not only is going to have a bigger aperture and a apochromatic refractor, but it's going to have 2 chips inside instead of just one. And 2 chips means you can do auto-guiding. Auto-guiding means you can do much more accurate guiding and do longer exposures, which is really powerful. And the other thing which is really cool is if you can swap between the chips, one chip is typically bigger than the other, you can actually change the field of view of your scope, which today with all the other scopes is a fixed thing. What you have is this focal length with this chip, and that's it. So that is going to be really interesting. And that's why I think that C-Star just has ZWO, the makers of C-Star, have the supply chain and the ecosystem that allows us them to do things faster and more creatively than anyone else. So I would keep my eye on that company. So, enough said about the electronic telescopes. Let's talk about real astrophotography. My stuff. So, this is my stuff. This is my rig. It's got the Astrophysics 900 mount, which is an equatorial mount. It's this little behemoth over here. Very accurate tracking of the night sky with auto-guiding support, so that you can really do hours and hours of tracking and stay focused on your object. This is obviously the telescope and that draw tube or focuser I mentioned. This is the electronic focuser control, and down here is the cooled camera. So this is what I use for deep space imaging. This cooled camera by ZWO, and we cool the chip down. I cool it down to roughly minus 20 degrees, and the reason we do that is it increases the sensitivity of the chip as we're collecting those very precious photons from space. It also reduces the readout noise of the chip, so that as I am saving the image, it's not introducing more noise into the image. Something we'll talk about image noise a little later. So this is basically the setup I use, and when you use a setup like this, you can start taking images like this. And the image above was taken by Stephen Kwong from our club. This is of the Rho Ophiuchi complex near the constellation of Scorpio. I haven't taken this image yet, it's on my bucket list, but Steve was kind enough to let me use his. And a very, very cool, it's about 2-hour exposure. The one down here is an image I took of the Crescent Nebula, which is a Wolf-Rayet star. Sorry?
It doesn't look like a crescent now.
It's a Wolf-Rayet star that is violently shedding off its material, and you can see a lot of very fine detail. This is about a 6-hour exposure. These kind of images are definitely outside the realm of possibility of the smart telescopes. You do need a dedicated setup to try and do these kind of images, and that's why it's still considered the gold standard for astrophotography. So let's talk a little about what it takes to take the different kinds of images. I'm going to check how I'm doing on time. Yeah, we're fine. So starting with a simple one, which is a nightscape. This is of the Milky Way from Fremont Peak. This was taken with a Nikon camera, ISO setting of 1600. This is a single 30-second exposure. There's no stacking involved. I did increase contrast in Photoshop, but that's the only thing I did. It was taken, I think, September of last year. September of last year. And what is really amazing in this image, and Daryl and I were talking about this earlier, you can actually see a lot of deep space objects in this image. So I'm going to zoom in a bit and call them out. There are 11 Messier objects of deep space images, deep space objects in this single 30-second exposure. We have here M7 and M6, as well as M23 and M25. These are all open clusters. We have the wide star field of M24. We have globular clusters of M22 and M28. And up here we have the Eagle Nebula, M16. Down here, M17, the Omega Nebula. And down here, the Lagoon Nebula. You can actually see the nebulosity there pretty clearly. That's just with a digital camera and a 30-second exposure. So again, digital cameras are pretty cool even for wide field attempts like that. The next image I have is another attempt with a digital camera, and this was taken from the tunnel view in Yosemite during a full moon, taken in September this year. And again, it's using the Nikon Z7 Mark II, 600mm lens. Now here the ISO is much lower, it's 100, and the exposure is only 0.2 seconds. The moon is thousands of times brighter than most deep space nebula and everything like that. So if I were to take a 30-second exposure, it would simply burn out the image. It would be just this big white blob. You wouldn't be able to see any detail. So you want to go really short and low sensitivity. And the trick of getting this, the trick of getting this silhouette in front of the full moon is all based on distance. You need to be at least 1.6 miles away from the object that's going to be in your foreground between you and the moon in order to be able to zoom in to get the full moon size and get enough detail and size of that silhouette. So these are trees up on the Three Brothers. If you're familiar with Yosemite and the view from tunnel view, that's what that is. Any questions on this?
You've got a mount for the camera, a tracking mount?
It was just a tripod, there's no tracking.
Okay.
It's 0.2 seconds. No tracking.
I meant for 30 seconds on the prior.
That one was, it was on the Ioptron Skywatcher, but it was turned off. So I wasn't tracking here either.
Actually, a question on that one too.
Yeah.
I've heard that like 24 seconds is usually the maximum you're going to shoot.
It depends. It depends on the lens. I think that at 20 millimeters, you have to go down to 24. It actually depends also if you have a full frame or an APC chip. So you have to. It's a combination of the length and the size of the chip that determines that. Yes.
What's usually the standard for the right amount of, concentration on the dark spots when you're taking a photo? You guys do like 15 seconds?
Well, as you can see here, 0.2.
Oh, 0.6. So it's really small.
Yeah, very short.
You have to time that up correctly?
Yeah, and the way I did it, I didn't come in with the knowledge of I'm going to be doing a 0.2 second exposure. I tried a 1 second and it looked like shit. So I went to half a second, it still looked pretty bad, and then I went down to 0.2 and I was like, oh, that looks good. Okay. So, moving on to solar system. And we're going to spend a little more time on solar system later in terms of processing. But just to explain what's going on here, the taking images of solar system objects, and in this particular case of the sun, is really tricky because these are super, super bright objects. And being able to image them means you need to take literally a fraction of a second exposure. But the problem that we're dealing with is we're not living in space, we're living with an atmosphere, and it's shimmering and moving. So if you take a really quick snap, you're just freezing some motion of the atmosphere. It's almost impossible to get a good image from just a quick snap of a solar system object, which is why we take many images and we stack them later. And the best way to take many images is through video. So here I use the ZWO 120mm camera. The telescope used here was the Lunt 100 Hydrogen Alpha telescope, which is currently kindly on loan to our club from Ken Lum's wife. And I took a 1 minute video with roughly about 30 frames per second. So it's about 1,800 images that were then stacked into this single image. And you can see a pretty nice granular structure in the surface of the sun and some nice prominences coming up here. We'll talk about the processing steps later. Let's move on to get away with 0.2 second exposures, 30-second exposures with the sun when you're doing videos. With deep space, you need long exposures. You need to take a lot of data because we're dealing with objects that are extremely faint. What we're seeing here is the Trifid Nebula, or M20, which is really a combination of 3 types of nebulae, I should say. The red stuff is an emission nebula, which is basically ionized gas glowing. This is basically where new stars can be born. The blue stuff is actually a reflection nebula. It's not generating its own light, it's reflecting light of stars. And the dark stuff is actually where all the interesting action is happening. That is dark molecular gas where new stars are being born. So when we talk about stellar nurseries, it's not the red stuff in the image, it's actually the dark lanes where the real activity is happening. This is a 4-hour exposure. It's over 50 images of about 5 minutes each. Now, for those who are not familiar with astrophotography, one may ask, well, why not just take 1 image of 4 hours? Well, if you do that, you're going to deal with a very high probability that a plane will go through your image, a satellite will go through the image, or there'll be a little glitch in your tracking, and now you've lost all 4 hours. So basically, you really want to break it down into smaller segments. So even if you lost 5 images, then you lost 25 minutes, but you've still got the other 3+ hours that you can then stack into your final image. And there are other reasons, especially living in light polluted areas. If you expose for too long, you're just going to overwhelm the chip. And you can all try that yourself. After you leave today, just stand on the rail outside, stand next to the rail outside, and lean your camera, your phone, point it to the sky, and do a 10-second exposure. And the sky will be simply white. And the reason is because there's so much light pollution that your camera is capturing that you can't see anything. So you also don't want to overwhelm the chip with too much light pollution. So let's talk a little about the processing of these images. And as I said earlier, in processing what I mean is how do we go from an image that looks like this to an image that looks like that? I'm going to take a sip of my tea and I'll continue. Better. Okay, so everything I'm going to discuss now is applicable to anyone who can access the raw data that they have, whether it's from a digital camera or a dedicated astronomy camera or from your smart telescope. So you can be satisfied with the output that the smart telescope just gives you, or you can be a little more adventurous, save your raw files to your machine and follow these steps. You might be able to produce a better image. So let's get started. There's a few do's and don'ts, or think of it as etiquette when it comes around to processing astrophotos. The first thing is you do want to remove noise. The nebula that you just saw and space around it have no noise. Any noise that's going to be in my image is self-inflicted and generated by my system. It could be generated by sky conditions, it could be by dirt in my optical train, it could be, and very typically is, from noise from the chip itself, the readout noise from the chip itself. There's various sources of noise that appear as graininess inside your image, and you want to get rid of that. So do remove noise by all means possible. The second thing is you want to sharpen your stars. You heard somebody earlier mention deconvolution is one of the ways of sharpening a star. Stars are supposed to be points of light, and they appear bigger than that simply because of the physical limitations of our chip. All this extra light spilling over to additional pixels around it. So we want them to be sharp. We obviously want our image to be as sharp as possible. If you took an image that's slightly out of focus, you want to sharpen it to get it as much close as possible to better focus. You want to increase contrast. You will see when we go into the live demonstration of the impact of contrast on the image, especially when you're living in the Bay Area, taking images through an incredible amount of light pollution, which is drowning the data you want in with data you do not want. And the next thing is, of course, color correction. So as we take images, we get distorted colors. They can be caused by the Bayer matrix that is in our one-shot color camera. They can be caused by filters. They can be caused by sky conditions, various types of light pollution. And there is the right way of correcting color, not inventing your own colors. So we'll talk a little about that. And then you want to remove any defects, because planes and satellites and such don't belong in your image, so you want to get rid of those. And then you want to improve and increase the vibrance and the saturation of your image. Again, I'm not saying let's color the image or let's add new colors in there. That's not what we do. But the color is already there. The problem is it's a very faint object, and we've got a very little amount of data to see that color. So as you'll see, what I do is I basically turn the saturation all the way up to 11. So I can get more color out of the image. And there's really only one cardinal rule about the don'ts. Don't add data. All right? We're not supposed to be drawing, copy-pasting, using AI to generate new stuff, because then that's not an astrophoto. It's some creative thing that you've done, and that's cool, but it's not an astrophoto. So in astrophotography, we do not add data. That's the most important cardinal rule. So let's explain the kind of fields that we take, or the images that we take. A standard image that we take is this light frame here. This is taken, by the way, with an old CCD camera. And this is the Horsehead Nebula and the Flame Nebula. This is about a 3-minute exposure, and this is what the raw data looks like. It's a single 3-minute exposure of the data. Now, the thing is, this image contains in it a lot of noise that I don't want. And so what we do is we image the noise, so then we can use software to say, all this stuff, I want you to remove it from my image. So the first thing is a bias frame. A bias frame is basically what happens when I switch on electricity. I'm not imaging, I'm not exposing light, just switched on the electricity, and just the fact that electricity is going through the chip is generating some noise. And I want to get rid of that. Now, that was an absolute requirement with CCD cameras. With newer CMOS cameras, the noise is significantly reduced. A lot of people say, you don't need that. I'm old school, I still do it. And so I do remove the bias data. The second thing is the dark frame. Now this is identical to the light frame. I just took a 3-minute exposure, but I kept the camera covered. So I'm exposing the chip for 3 minutes. It's running current. It's trying to collect light. And what I'm capturing here is any ambient noise or hot pixels the chip may have. Sometimes you have a pixel that's defective and it appears as a hot dot in your image. That will be registered in that image. In this particular case with the old CCD, you can see there's this little gradient here. That's called an amp glow, which is basically some heat generated from the camera and is being faithfully recorded by the chip. That noise is in my image and I don't want it there. And last but not least is the flat field, which is basically exposing the chip to a evenly illuminated field of view that allows me to detect any optical imperfections. If it's dust on my camera, dust on my lens, that I don't want there. And actually, if you pay attention, you can see in this flat field, there's a little dark dot over there. With some attention, you'll notice it's right there in the image, that dark dot. So basically, what I'm doing is I'm taking, when I calibrate my image, I take my light image and I reduce all this noise. I image this noise and then take it out of the image. Okay? And if you're curious about how a flat field is taken, so this is me taking a flat field. This is my scope, and there's a little white light that is giving me the flat field, that evenly illuminated view. So, moving on to what we do here is we are reducing this data to create a single nice clean frame. And if I took 50 images, I'm going to be doing this 50 times, because I need to clean up all those 50 images before I stack them. And the reason we stack them is because we want to improve the signal-to-noise ratio. Now, signal-to-noise ratio simply is signal, that's the data I want. That's the photons of that, of the nebula or the galaxy or whatever it is I'm imaging, and the noise is everything else that I don't want. So I want to improve the signal-to-noise ratio, as much signal as I can, and reduce the noise. This is how I do that. Now, in most applications these days, this is an automated process. What I'll be showing you here today is based on PixInsight. This This is a good opportunity to say thank you to Frank Seminaro, who 2 or 3 years ago convinced me that I should join the rest of the 21st century and start using real good tools. And wish I'd done that earlier. There's lots of great software solutions out there. There's CCD Stack, there's Deep Space Stacker, there is Serial, there's lots of tools. Some of them are free and very good. I swear by PixInsight, I have not seen a software package that has such granular control over my image processing. And it's not free, but I think it's worth every cent. So what we see here is the automated process in PixInsight, where all my 50 images, my light images are in here. From all 50, it will reduce the bias, the darks, and the flats, and then it will stack them to get my final image. That's the process. Okay? So now, let's explain at a high level what the steps are. And these are the steps I use in PixInsight. It's the most recent variant of the process that I use. I've been using it, I think, about 6 months ago. I kind of stabilized on that. I keep changing all the time. So this is what currently works for me. And it's important to understand that when it comes around to image processing, there are 2 very distinct phases. There is linear processing, and then there is non-linear processing. Linear processing simply means that whatever change I'm doing to my image is going to be done equally to the entire image. Okay? The whole image is going to be affected the same way. That's why it's called linear. When it's non-linear processing, it means I'm now taking selective parts of an image. A selective part could be physically an area in the image, or it could be just a subset of the histogram that I want to play around with, and I'm now doing non-linear changes to the image. It's really important to do these in these phases, because if I went and did non-linear changes and then tried to go back and do linear changes, I will create really strange artifacts in my image, and you want to avoid that. I'm going to quickly go through this list, and then we're actually going to explain this in the tutorial as we go in. SPCC stands for Spectrographic Color Correction, which is a really cool tool. It is basically a connection to a scientific database that has used all the spectral analysis of all the stars and objects in space that we know of, and measures them against my image, and corrects the color that way. So when it's doing color correction, it's doing it based on real scientific databases rather than what I think looks okay. The cropping is simply to remove any stacking artifacts I might have on the edges of my image and allow me to center my object. StarX is a very cool AI tool to remove the stars, and you will soon see why getting rid of the stars from your image is absolutely critical for deep space imaging processing. So we'll talk about that in a minute. Gradient X removes the gradients. Again, if I have a gradient in my image, which means that one area of the image is more illuminated than the other, let's say because of vignetting. For those that don't know what vignetting is, if you have a rectangular chip of your camera and you're taking a picture through a round telescope, so you have the light not falling in a even way on that rectangular chip. So that can cause vignetting. And if you have gradients in your image, if I now, let's say, go and increase contrast, it will not do that evenly in the image. So you want the image to be evenly illuminated. Getting rid of gradients is important. BlurX is an AI tool for sharpening, which we'll talk about in a minute. NoiseX, another AI tool that reduces noise in the image or graininess from the image. And then stretching or screen stretching, which is basically me clipping the data, looking at the histogram, and bear this in mind. When you have an image, let's say this nebula, that nebula, if I were to look at it, the histogram of the image, sits in maybe 5 or 10% of the data of the image. All the other 90% of the quote-unquote data in this image is noise, light pollution, stuff that I don't want. And so that's a very important way to really improve the contrast of the image. And then we go into non-linear processing, which is selecting different parts of the image if I want to increase saturation, want to increase contrast, and do those steps there. So let's jump now into the actual steps one by one. And hello, there we go. So there is my final image. Looks great, doesn't it? So you can see that there's a nebula over there, hidden in all that green stuff. And you may well ask, what the hell is all that green stuff? So after I've calibrated my images, all those 50 images, I've taken out the bias and the darks and the flat frames, and I've stacked them. This is my final outcome, rather disappointing, isn't it? So basically, this is a one-shot color camera, and it has a bare matrix. And that little matrix on every pixel has 2 green filters. So it's skewing the image towards the green. Now this, by the way, this effect can be made worse if you're using certain types of light pollution filters that can actually accentuate the problem. So the first thing I want to do is to color correct this image. And remember I told you about the spectrographic color correction. It knows that this is the Trifid Nebula. It knows the spectral data for each one of the stars in my image, because it's connected to this very broad database. It knows the time and place the image was taken, and it will go and match the data and correct it accordingly. And in the past, I would use this thing called dynamic background extraction, which would, I could sort of mark a little area and say, that's space, to get rid of all the stuff in that area that isn't, space. And it would remove all the green stuff, but it would actually mess up the colors and create an inaccurate image. So running SPCC produces this image. So that already starts to look a little better, because I can now see my nebula, I can see the stars, and space is no longer green. So that's one good step. The next thing I'm going to do, if you remember, is I'm going to get rid of the stars. Now, before I get rid of the stars, I'm going to remind you a couple of things. Number one, in astrophotography, we don't add anything, we only remove things. Secondly, the engine, the AI engine that is used here, StarX, was specifically designed for astrophotography. So the data model it has was trained on space images, so it kind of knows what it's doing. It's not perfect, but it does a pretty good job. And before I show you the result of this next step, I want you to pay attention to what you can see in the nebulosity here right now. And now take a look at the image without the stars. It's the same image. It's the same image, nothing was added, but take a look at all this detail that now you can see in the nebulosity over here that you can't really see here. So why is that? The reason is our brains. They're limited. Now, by show of hands, who's ever looked at the blinking planetary nebula through a visual telescope? Okay, thank you. I'm getting depressed here, all these smart telescopes. So, if you've ever used a 10-inch or 8-inch or 6-inch telescope and looked at the planetary nebula called the blinking planetary, it is a small little faint nebula. And when you look at it initially, it's right there, and then when you pay closer attention and you're looking at the very bright central star of that nebula, it disappears right before your eyes. And then you look away and you look back and it's there again, but if you really focus on looking at it, it disappears. What's going on here? This nebula obviously is not disappearing and reappearing before our eyes. It's our brain. Our brain cannot process the high dynamic range of these data points. The very bright star in the middle and that faint nebulosity around it, it's going to focus on that really bright star and kind of ignore the nebula. And it disappears before our eyes. This is exactly what's happening inside this image. All this nebulosity that we can easily see here, we cannot see well in this image. We can see the brighter parts. But take a look here, you can just barely see a little bit. And look how much is going on here. And the reason is because all this stuff is competing with these bright stars. And our brain cannot process it. So we can't even really see what's in our image unless we got rid of those stars. Because now we know what we're working on. The other reason we're taking out the stars is not just to better see what we're doing here, but when we're going to do all sorts of changes to this nebula and to this image, we don't want to affect the stars. If I'm going to increase contrast, I don't want all the stars to become even brighter than they are already. So I'm going to treat the stars separately. Take them out of the image, focus on your targets. Now, the next thing I'm going to do, and it's not going to be very noticeable, I'm running the gradient removal. If you take a look, there's a little brighter area than here. There's not a lot of gradient in this image. So you will see that this image is more evenly illuminated, but it's not a big difference between the two. Okay? Now, the next thing we're going to do after the gradient removal is a little bit of sharpening. And again, here we're using an AI engine. This is called BlurX. And this was again trained on astrophotography data, so it's designed specifically. It's not a generic Photoshop improvement of sharpening, but really designed to handle deep space objects. And the first pass, it doesn't look like a lot, but actually it's really improved things. I'm going to show you. Pay attention to the dark lanes over here, and look at them over here. The edges are definitely more defined. The dark nebulosity over here is popping out a lot more than here. The details that I can see in this cloud are much clearer than here. It's done a very small but meaningful change to improve the quality of the image. Now, when I did the real processing for that final image you saw earlier on, I probably ran this 3-4 times. But for the purposes of creating these screenshots, I just did it once. So it's absolutely fine to run sharpening 2, 3, 4 times. But bear in mind, every time I'm sharpening, I'm also introducing noise into my image. So I'm going to have to deal with that. It's not very prominent on the screen here. If you were to look on my laptop, you will see the noise in the image, especially in the open areas. There's a little bit of noise here, and it's made a little worse over here. Again, I know it's hard to see on the projection. On a computer screen, it really jumps out. And so when we run the noise X reduction, it will smooth out the image, and now these areas are much smoother. I know that, again, hard to see the graininess here, and therefore hard to see the difference, but on the computer screen, it is quite noticeable. So removing noise is really, really important. Now we take this noise image, and the next thing I want to do is I want to, I think it's the screen stretch. So pay attention to the image, and I actually want to show you something here. I don't know if you can see there's a bit of nebulosity here and a bit of nebulosity there, very faint, very hard to see. But over here there's nothing. Over here is space. That is not the color of space. Space is not a light gray place. All right? So what is this gray stuff? Sorry?
We have to cut it out soon. Unfortunately, we have to go in a little bit.
5 minutes?
Yeah, but I can give you 5 minutes. It's just a bit of an emergency, that's all.
Okay. Wow. Okay, I'll try and dash through this. So basically, all this gray stuff is light pollution. It's basically all the lights of the cars and the houses and the street lights that are shining everywhere, hitting the atmosphere, and hitting molecules in the atmosphere and then shining back at us. We don't want that. So I use the screen stretch to clip the data of the histogram. And again, I'm reminding you, we're not adding any data. In fact, I'm removing 90% of the data in the image, and take a look at what happens. Now this nebula is popping out, and I'm reminding you, I didn't even increase its contrast. I didn't increase its brightness. I didn't do anything. I just took a gray screen, because I was basically looking at this faint nebula in space through a gray screen of all this light pollution. I got rid of that data, and now this thing really pops out. The next phase that we're going to do, and we're dashing here, is a little improvement of the contrast. So basically selected just the nebula, not to affect the background space, and just increase the lightness just a little bit. And then, this is my final image. As I said earlier, it's got color in it, but the color is subdued because I only did 4 hours and not 40 hours. So what I do here is basically I take the saturation knob and turn it all the way on to full, not introducing new colors, but increasing the volume of the existing colors, and I get this. Now, I did a lot more work on my real final image, but for now we'll call this a good final nebula. I still need my stars. The stars are in a separate image, so let's treat those. There is my star image, and you can see that they're pretty bloated. They're not points of light. We ran a sharpening stage, which brings them a little more tighter. This is sort of the deconvolution phase, if you will. But we can also do a little better job using screen stretch and a thing called morphological transformation. And this basically looks at minor imperfections in your star and tries to round them out. It can't fix bad tracking. If you've got trails, in your image, that's not going to help. But small imperfections, it can improve. And there now is my final image. So I have my final image of stars, I have my final image of the nebula, and next I combine them using pixel math, and there is my final image. Okay? So these are the steps that I took to process this, this image. Now, remember where we started? We started with this. Okay? It's the same image. And when you think about what we did, we basically, most of the actions we did here was to delete stuff. We deleted the noise, we sharpened a bit, we deleted the light pollution, we increased the contrast, and we increased the saturation. That's all we did. But by doing it separately and doing it, the stars and the nebula separately, we're able to get pretty good control and produce a nice, compelling image. I'm gonna use the last minute I have to talk about this slide, and it's my last slide, which is processing solar system objects. As I mentioned earlier on, I cannot take a nice, quick snap of a single image of a solar system object because of the brightness, which means it has to be a very short exposure, and I'm doing a short exposure on the moving atmosphere. It doesn't work. So what I do is I take a video. And typically, I'll take a video with cameras that can do anywhere between 30 to 60 frames per second, and take about 2 minutes. So I might have 5,000 images. And free application you can use for that is SharpCap, has a lot of controls that you can use. Then stacking. There's Registacks that you can use. I actually recommend AutoStacker, which is a free software, which will take your image. It will analyze the best images that you have out of those 5,000 and which ones are in better focus, and then it does a mapping of your image, these little tiles, overlapping tiles, and it'll analyze the focus of each one of them to compile a final stack of one image with the best focus it could find across thousands of images, producing your final image. This one is of Saturn and of Jupiter. And then you want to sharpen it. Sharpening is a little different. Instead of just applying a sharpening process to the entire image, the applications that I mentioned here, like Registax and IMPPG and NAIF, they actually have different levers or controls that allow different sharpening processes to different levels of detail in your image. Large objects or large areas of the image, fine, small areas, and we will sharpen each one of them separately, allowing you to play around with the levers to find the best balance and the best sharpened image you can create. And then that final image is taken to whatever software you like to improve contrast and color balance. Those are the steps to processing, and that's what I did with each one of these images. So sorry this last few minutes was a bit rushed, but we have covered everything I intended to cover today, and I'm way open to questions unless we get kicked out.
Sorry, I can't do questions.
We
Leave.
My apologies.
Sorry guys, I'm having a bit of an emergency, so I'm gonna have to close up pretty quick here. Thank you guys, I'm so sorry.
All right.